So in this lesson, we're going to be talking about voltaic cells. And so this is a voltaic cell, and I'll explain how it works in just one second. But one of the main things for you to recognize is that when these redox reactions occur, which we studied in the last section, energy is going to be released, and energy is released in the form of electrons. We actually looked at that when we were balancing redox reactions, noting that you're going to have electrons produced and then you're going to have electrons accepted. So there's a movement of electrons. And so what a voltaic cell is actually a device that, rather than just allowing that redox reaction to occur in a solution, what it does is it separates out the reduction reaction and the oxidation reaction, and what that allows us to do is to have the transfer of electrons that occur actually happen in an external pathway. So the electrons are going to be moving outside of the solution, which then enables us to be able to use it for actual power, for electricity. But we're just going to be looking at the reaction that occurs, accepting the fact that electrons are going to be moving through that wire up top, and therefore that the electricity that moves through it can actually be measured, and so we'll talk about that as well. In a voltaic cell, there are going to be two solid metals, and so if you notice here, you've got zinc and you've got copper solid metal, and so for these two solid metals, they are called electrodes, and so the electrode that has oxidation occurring at it, that's called the anode. So in this case, that's going to be the zinc metal, that's the anode, and then the cathode is going to be the one that has reduction occurring at it, which will be the copper metal. And each of the beakers represents a half cell, meaning in one of them oxidation is going to happen, and in the other one reduction is going to happen. So I'm going to show you really quickly, I'm going to explain how this voltaic cell works. So if we look first at zinc, what's going to happen, and you can see this in the reaction, zinc is actually going to be oxidized to become zinc with a +2 charge, and it's going to release electrons. So the zinc solid is actually going to slowly but surely break apart to become zinc ions, and so the size of that metal solid is going to decrease, and as it decreases, producing zinc ions, the electrons move up and to the right all the way across to the copper metal. Now the copper metal accepts those electrons, and what actually happens, if you look, the electrons are actually going to transform the copper ions that were in solution to copper solid. So that copper metal, that solid, is actually going to grow in size as copper ions become copper solid. The important thing for you to know, looking back at these two solutions, you've got the grayish solution right there, that is zinc sulfate, and then you have copper sulfate on the other side. So ultimately what's happening is zinc ions are produced while zinc solid is used up to produce those zinc ions. The electrons move all the way across, and then what that allows the copper ions to do is to become solid copper. And so what you should be realizing is that while on the left-hand side you're producing more and more zinc ions, on the right-hand side, you're producing more and more copper solids, so you're getting rid of the copper ions, which creates a problem because at a certain point, if you have a lot of zinc ions and very few, if not none, copper ions, then that's going to cause a difference in charge, which will then prevent that voltaic cell from working. And so the last component of the voltaic cell here is the salt bridge. Now the salt bridge contains an electrolyte. It doesn't actually react with any of the other ions, but it provides cations and anions in order to neutralize the half-cell solution. So if you notice here, on the left-hand side, you have plenty of zinc ions, and so nitrate is going to go in there to help neutralize the zinc ions so you don't end up with a huge positive charge on that side, on where oxidation is happening. On the other side, on the right-hand side, where reduction is happening, sodium ions are put into solution because otherwise you would end up losing a bunch of positive charges because they're becoming copper. And so sodium is then put into that solution to prevent it from becoming negatively charged, since you're just left with sulfate ions in the solution because you're getting rid of copper ions. And the last thing you need to notice is the fact that the anode has a negative charge while the cathode has a positive charge. And so this doesn't really at first make sense because you're losing electrons from the anode and they go to the cathode, so why wouldn't the anode be negatively charged? Well, the reason why is because electrons are going to move towards a positive charge, and so therefore we say that the cathode is positively charged, and therefore the electrons move towards the cathode. The first question you should ask, we know that electrons are transferred spontaneously. once we create a voltaic cell, or once we create a solution in which reduction and oxidation happens, we don't need to do anything. It will occur automatically. So the question is why? And the answer to that question is potential energy. And so when we're thinking about cell potential, which is the potential difference between the two electrodes, the best way to think about this, because this is a little bit abstract, is to think about a waterfall. We know that water is going to fall from the top of a waterfall to the bottom. That's obvious to us based on gravity. Same thing for cell potential. It's that potential energy between the two electrodes, and therefore that's why the electrons are going to move spontaneously from the oxidation reaction to the reduction reaction. And so we're going to actually quantitatively represent this cell potential, and so it's labeled as E cell, and if we're at standard conditions, then we show that not symbol. And for standard conditions to be met, you're either, if you have a gas, you're at 1 atmosphere. If you have a solution, it's 1 molar concentration, and then you're at 25 degrees Celsius or 298 Kelvin. The units for cell potential are going to be volts. So volts, the unit for measuring this potential energy difference, it is the difference in potential energy per electrical charge. And so 1 volt equals 1 joule per coulomb. And then just one more term that we use when we're talking about cell potential is the electromotive force. Now that concept results from the fact that the potential difference between your two electrodes causes the electrons to be pushed. So it's an electromotive force that pushes the electrons from one electrode to another electrode. All right, so a couple of conventions when we're talking about cell potential. First, the half cell potential is going to be listed actually as the reduction potential only. So these values will be given to you. So it will be E reduction. We're not given the values for oxidation. And so if you have a substance that's going to be oxidized, all you have to do is multiply the standard reduction potential, the value that's given to you, the E reduction, by -1. So just make it a negative number, and there you've got your standard oxidation potential. And finally, if a reaction is going to be multiplied by a coefficient, you actually do not multiply your E reduction by that coefficient, unlike what we've done before, for example, with entropy and enthalpy. You don't multiply, so you just leave it as it is. So I'll show you some examples in just one second. The last thing I wanted to show you was the equation for determining the cell potential. And so what you do is you take the oxidation potential and you add to that the reduction potential. And so when you add those two together, there you will get the cell potential. Cell potential is simply the potential difference between your two electrodes. Where this is useful is for a reaction, if it's going to be spontaneous, then its net cell potential is going to be a positive value. And therefore, the more positive the cell potential, the more likely it is to occur. And if you think about this, if you have a very negative cell potential, when you're talking about reduction potentials, that means that the reverse, the oxidation potential, is more likely to occur. So here's an actual calculation for a problem. The first thing you have to do is you have to identify the oxidation and reduction reactions. Well, H2 goes from being H2 with an oxidation number of 0 to H plus with a plus 1 oxidation number. Therefore, it is being oxidized while fluorine is being reduced. And so what you need to do is you need to look up in your table, and it's actually in your textbook on page 841. If you look it up, the reduction potential for hydrogen, all of these values were actually based on one initial value that was given, and so that actually was for hydrogen. And so they set that reduction potential at 0. So hydrogen happens to be at 0, but if you looked it up, notice this is oxidation. So let's say, for example, the reduction potential were 2, then the oxidation would be -2. Okay, but here it's 0. Okay, for reduction, if you look up for fluorine, it's 2.87 volts. And so you would simply add these two values together and you get 2.87 volts for your standard electromotive force or for your standard cell potential.